Hi children, this is Shrenu, I teach physics. Today we are going to discuss about center of mass of hemispherical shell. Already in the previous classes we discussed about center of mass to the ring, disc and triangular lamina also. But now in this class we should discuss about center of mass to the hemispherical shell. Let us come into that. Okay, right, this is the hemispherical shell. To this hemispherical shell, if you want to find out the center of mass, you will have to know some information. Actually, the hemispherical shell looks to be, it's like a bowl. It's like a bowl. If you invert that bowl in that shape, this hemispherical shell will appear to us. Okay, clear? But where the center of mass is located in this hemispherical shell, on the x-axis or y-axis? Of course, on y-axis, the center of mass is located. Because of the reason, on either sides of this y-axis, the mass is distributed uniformly. Okay, not from y-axis, from the not from the x-axis. From x-axis, mass distributed not equally. But on the y-axis, on either sides of the y-axis, mass distributed equally. So that is why center of mass will be located on the y-axis. Know that very clearly. And of course, actually this is a continuous body. To the continuous bodies we cannot find center of mass directly. So then what do we have to do? We should take small elemental masses. So that is why I am going to take small elemental mass from this hemispherical shell. That small elemental mass should be as ring, not a disc. Actually this is not a solid hemisphere, solid hemisphere. This is actually hollow hemispherical shell. So whenever you take the hollow hemispherical shell, from that you can get only ring. Okay, clear? I am taking here elemental mass as ring. Okay, this is the small elemental mass of the ring. This is the ring. Okay, this is that. So this is the shape of the ring. This is the small elemental mass of ring dm. Okay, dm mass I took. Okay, and the total mass of this hemispherical shell is capital M, remember, and the radius of this hemispherical shell is capital R, and I am taking the radius to the small elemental ring also, that is here smaller. Smaller is the radius of the ring, small elemental mass of the ring, and capital R is the radius of this hemispherical shell. And if you see the center of mass of the ring from this origin is located at y distance, means y is the distance of center of mass of the ring from here. If you integrate this y from here to here, what will come? You can find the center of mass to this hemispherical shell. So that process only now we are going to do. And at the same time, I want to take the position of this elemental mass of the ring from origin. From origin with x-axis is pi. At an angle pi, the position of the elemental mass of the ring I am taking with x-axis. Let me tell you once again, the position of the elemental mass I am taking at an angle pi with x-axis, and the angle of this small elemental width of this small elemental mass as d pi. D pi is the angle of width of the elemental mass. So let me tell you, here d pi is the angle of the width of the ring and pi is the position of the elemental mass at an angle pi with x-axis. Remember that. And I am taking pi angle here also because of the reason these two are the alternative angles, and this length I am taking as capital R. But if you observe this figure, there are three variables you can observe. One is y, second one is r, and next one is pi. These three are the variables. How can you say? If you take this ring at the bottom, I wish to tell you once again, if you take this ring at the bottom, then what will happen? This smaller will become capital R, angle pi will become 0, and this y will become 0. But I did not take at the bottom, but here at the distance y I took. In case we are taking at the bottom like that, you will have to take. R will become capital R, small r will become capital R, pi will become 0, y will become 0 when you take this ring at the bottom. In case In case if you take this small elemental mass at top of the hemispherical shell, what will happen then? This r will become 0, y will become capital R, pi will become 90. It means what? The angle pi is changing in this hemispherical shell from 0 to pi. Sorry, not 0 to pi, 0 to pi by 2 at 90 degrees. It is changing from 0 to pi by 2, 0 to 90. Clear? The angle pi is changing from 0 to 90. Right. Next one you see. But actually here there are 3 variables are there, but I want to convert all in one. I want to take only one variable. Here 3 variables are there. It means what should what I want to do? I want to convert the small y and r into pi angles. I want to convert the small r and capital small y into pi. Here these 3 are the variables. I am converting these 2 variables into pi. How is it possible? By the trigonometry it is possible. Just you see, if you take the sin pi, opposite side is y, hypotenuse is capital. Finally what will come? Y is equals to r sin pi is coming. What did happen? I converted y into pi. Then after I am taking cos pi. Cos pi is equals to, adjacent side is smaller, hypotenuse is capital R, small r is equals to capital R cos pi. Here I got y value and small r value. Y value as r sin pi and small r as capital R cos pi. But if I want to find the center of mass of this hemispherical shell, I want to find out small dm also. Without finding out the small elemental mass, we cannot find the center of mass. So then what should we do? I want to find out the small elemental mass dm. That is possible by dm by dA is equals to m by a. I think so might have understood. Small elemental mass by small elemental mass of the ring area, total mass by total area. But my aim is I want to find out this dm. So then you write dm is equals to m by a into dA. Okay, clear? Then you write dm is equals to m. Here a is the capital A is the area of the hemispherical shell. If you take the complete shell 4 pi r square, but we are taking what here? Half of the hemispherical shell. That is why you do the 4 pi r square by 2. That is 2 pi r square. What is coming? 2 pi r square. And now the dA is the area of the small elemental mass of the ring. What is the area of the ring? Length into width. Here width also there. Here width is, this is the width of the ring. Width of the ring is how much? Width is equals to r into d pi. Okay. Width is equals to r into d pi. Already we know the formula of the angle formula. Okay, clear? So then you write arc by radius. Arc by radius is the angle formula. So that is why I am taking width of the elemental mass of the ring is r into d pi. And the length of this ring is 2 pi r. So you write here dA is the length into width. Length of the ring is how much? 2 pi small r, and width is how much? R d pi. R d pi. So here 2 pi is get cancelled, and here small r capital R, here one capital R get cancelled. Finally you can write dm is equals to what are there here? M by r, small r into d pi. Then dm is equals to capital M by r into, here what is small r? Small r already we found as capital R cos pi. Capital R cos pi into d pi. Then you write here capital R cancel. Finally dm is equals to, you can get capital M cos pi d pi value is coming. Okay, successfully we found the small elemental mass of the ring dm also, that is capital M cos pi d pi. Then what is our aim next? I want to find the center of mass of to this hemispherical shell. So already in the previous classes we knew, okay, according to method of integration, how do we have to find out the center of mass? That is ycm is equals to 1 by capital M into, integral ydm. Let's write now ycm is equals to 1 by capital M integral this variation here, y is changing from where to where? From 0 to 90. Here the value of y is changing from 0 to 90. Then limits also I am taking from 0 to pi by 2, nothing but 90. Here what is y? Y is r sin pi. R sin pi into what is dm? Dm is equals to capital M cos pi d pi. It's very clear. Then you write y center of mass. Here capital M is cancelled, bring r outside, and next you write sin pi cos pi d pi, limits from 0 to pi by 2. Okay, if you take the sin pi cos pi, it links to be according to trigonometry. What you can write here? YCM is equals to capital R into limits from 0 to pi by 2 sin 2 pi by 2 into d pi. How can you write this? Is already we knew. Sin 2 theta is equals to 2 sin theta into cos theta. This you can be modified as sin theta into cos theta is equals to sin 2 theta by 2. Like this. In this model you are writing. Here already what are there? Sin pi cos pi is there. That I am writing as sin 2 pi by 2 in the form of sin theta cos theta is equals to sin 2 theta by 2. Like that. Okay, clear? Then you bring 2 outside. YCM is equals to r by 2 integral sin 2 pi d pi 0 to pi by 2. Okay, what is the integral cos theta? Integral cos theta is equals to minus cos theta. But actually here what is there? Sin 2 pi is there. So finally what you can write here? Minus cos 2 pi. Again we will have to do the 2 pi as differentiation. Okay, that will come. What will come then? 2 will come. So by 2. So then you write YCM is equals to r by 2 minus cos 2 pi by 2, limits from 0 to pi by 2. Okay, then you write y center of mass r by 4 minus also I am bringing outside, minus r by 4 cos 2 pi, limits from 0 to pi by 2. Okay, right? Then YCM is equals to minus r by 4, upper limit minus lower limit. Here in the place of pi, if you substitute pi by 2, what will come? Pi only will come. So cos pi minus cos 0. So then you write y center of mass is equals to minus r by 4 of minus 1 because of cos pi is equals to how much? Minus 1. Cos 0 is equals to how much? 1. So minus 1 will come. So finally what you write here? Y center of mass minus r by 4 minus 2 will come. So here one time, this is 2 times. Then y center of mass is equals to minus into minus plus, and finally you can get r by 2. So r by 2 is what here? Center of mass of this hemispherical shell. Finally I think so you might have understood by this integration process you are getting y center of mass as r by 2. So when you are taking this hemispherical shell, if you want to find the center of mass, by this process you can be done, and you are finally getting r by 2 value. Okay, please all of you note it.